In the last lesson, we learned that 5G networks will speed up the pace at which we adopt cloud VR in our daily lives. Today, we are going to talk about something that we see every day: vehicles. Research shows the number of vehicles worldwide exceeded 1.3 billion in 2018. Vehicles may become the second most used mobile smart devices after phones. Internet of Vehicles, or IoV, has sensors, controllers, and actuators, and integrate modern communications and network technologies to enable the sharing and exchange of information between vehicles and vehicles, or V2V, vehicles and infrastructure, or V2I, vehicles and passengers, V2P, and vehicles and networks, or V2N. IoV vehicles are capable of perceiving complex environments, intelligent decision-making, and implementing coordinated control to realize safe, efficient, comfortable, and energy-saving driving. Ultimately, human drivers will be substituted by a new generation of self-driving vehicles. IoV has a very promising future. Industry players are currently trying to grab IoV business opportunities and market share. In this lesson, we are going to look at some of the interesting applications of IoV. IoV will be important for enabling smart transportation in the cities of the future. For example, clearing driving pathways for emergency vehicles. Ambulances can broadcast the longitudes and latitudes of their routes through V2V systems, so that other vehicles can give way in advance. At the same time, ambulances can communicate with traffic light control units via V2I to adjust traffic light duration in a way that makes it easier for ambulances to move faster. To the patients being transported in ambulances, reaching the hospital 1 second sooner might be the difference between life and death. Another application of IoV is collision warnings at intersections. Some intersections have sharp turns or have drivers' view blocked by buildings, which makes it impossible for drivers to see vehicles or pedestrians at the intersection. In these cases, V2V and V2P systems allow drivers to obtain information about the traffic situation at the intersections, allowing them to make any needed preparations in advance, and coordinating traffic between vehicles and passengers, and between vehicles and vehicles. Two other applications of IoV are remote driving and automated driving. Remotely controlled drones are now common and are widely used in multiple fields, such as aerial photography and inspections. But have you ever seen a vehicle that is remote controlled like a drone? In the future, people will be able to remotely drive their cars from hundreds of miles away through the internet. Even vehicles will be able to drive themselves using the internet and their own sensors and control systems. This will completely revolutionize how people travel. IoV will also make it possible for automobile manufacturers and insurance companies to provide custom services for drivers based on data such as driving habits, driving speeds, frequency of abrupt braking, and invisible vehicle malfunctions. IoV can currently be divided into two broad categories: Advanced Driver Assistance System, or ADAS, and Cellular Vehicle to Everything, or CV2X. Next, we'll take a closer look at these two technologies. ADAS is already used commercially. Vehicles with ADAS have cameras, radars, lasers, and ultrasonic sensors that use light, heat, pressure, and other variables to monitor a vehicle's state. ADAS functions include blind spot detection, lane departure warning, lane keeping assistant, and collision warning. However, single vehicle smart technologies like ADAS have weak interactivity, and their sensors have limitations. For example, such systems are affected by rain, snow, and fog. Their detection distance is also short, and they are expensive. CV2X is a technology that connects smart vehicles through cellular networks. CV2X uses cellular networks to transmit information collected by vehicle-mounted sensors to surrounding vehicles, roadside infrastructure, pedestrians, and the cloud. Through this, CV2X connects vehicles to everything else. CV2X is currently categorized into 4G LTE V2X and 5G V2X, which will be introduced in the future. CV2X is relatively cheap to deploy, as it can make full use of existing 4G and 5G industry ecosystems. CV2X also has following advantages over ADAS. Driving vision. CV2X uses 360-degree internet-connected cameras to observe a vehicle's surroundings. This allows a driver to see their surroundings without having their view blocked. Detection distance. ADAS can only detect a vehicle's surroundings within a range of 100 meters, while CV2X can detect up to 300 to 500 meters. This allows CV2X to detect danger more than 10 seconds earlier than ADAS. Price: CV2X is cheaper than ADAS. ADAS costs hundreds or even tens of thousands of US dollars, while a CV2X module only costs tens of dollars. Weather impact. CV2X is not affected by the weather, but ADAS's reliability is affected by rain, snow, and fog. CV2X can also achieve collaborative intelligence, which is more effective than ADAS. From what we discussed, we know that CV2X can solve the problems invisible and unclear to ADAS, but ADAS is a more mature technology. Research on 6 million traffic accidents shows that combining CV2X with ADAS can reduce traffic accidents by 96%. As such, integrating ADAS with CV2X will be the best option for future IOV. Our examination of future CV2X technology has touched on how it needs to be connected to the internet. CV2X's specific network requirements are as follows. High traffic. Each vehicle will use 4,000 gigabytes of data each day. Also, cloud devices supporting CV2X must have strong real-time computing and analysis capabilities. Latency. End-to-end or E2E network latency must be less than 4 milliseconds for optimum remote vehicle control. Connectivity. In the future, V2V, V2P, and V2I will generate many connections, which will increase exponentially as the number of vehicles grows. CV2X's network requirements can be summarized as high data rates, low latency, and massive connectivity. Can 5G networks meet IOV's demanding requirements? Yes. Let's take a look at what 5G can do. .5G networks can provide different high-speed and low-latency network slices to different IOV services to guarantee data transmission between vehicles and the cloud. 5G V2X edge computing cloud servers can also be deployed on the 5G radio access side to support services that have high data volume, real-time processing, and computing complexity requirements. 5G networks also support simultaneous connection of different interfaces. IOV requires networks with low latency, high reliability, and support for broadcasting and multicasting. 5G networks can meet these requirements. 5G V2X also supports combining UU and PC5 interfaces. Data generated by vehicles can be transmitted to 5G base stations through UU interfaces. The 5G base stations then forward the data to the rest of the network. For transmission over short distances, vehicles may directly commute with target devices via PC5 interfaces, relieving pressure on the base station and reducing data transmission latency. 5G networks also support unicast multicast latency optimization. Unicast latency optimization technology determines the type of vehicle service to pre-schedule data and semi-statically allocate services. This pre-allocation of resources reduces data transmission latency. Multicast technology is agile and can be used to group vehicles with the same service requirements. Multicast technology allows a shift from independent scheduling of vehicle data to simultaneous scheduling of multiple vehicles' data after they are sorted into groups. This reduces base stations' scheduling resource overhead and greatly increases base stations' connectivity. The advantages of 5G networks that we have discussed will provide robust support for future C-V2X development. It's likely that future vehicles will be intelligently connected. Through 5G networks, vehicles will exchange data with the cloud, pedestrians, and other vehicles. This will allow better coordination between people and vehicles. Roads will also become digitized and more intelligent. Ultimately, people, vehicles, and roads will form cooperative systems that will revolutionize future transportation.